Assistant Professor in the Department of Civil Engineering. Today we will be going to discuss about a topic, Introduction to Hydraulic Machines, Turbines. So first of all, before getting into the session, everyone has to have a basic knowledge of what is a machine and what is a hydraulic machine. So first of all, machine is a device which will simplify any kind of a work. Hydraulic machine is the machine or a device which are conversant with hydraulic structures or mostly with water presence. So in hydraulic machines, so there are two types of hydraulic machines. So one is turbines and the another one is pump. So if you take a hydraulic machine, so in turbine, these are the contents. So layout of hydroelectric power plant, introduction to turbines, and classification of turbines and efficiencies which are used in turbines. So first of all, what is a hydraulic machine? So we already discussed the basic of what is a machine. Machine is a device which will simplify the work. Hydraulic machine are the devices which are conversant with water or which are used in water relevant structures such as in irrigation structures like dams, power plants, etc. So in hydraulic machines, in civil engineering, we are mainly deals with two types of hydraulic machines. One is turbines and the second one is pump. So in coming to the basic of what is a turbine, so turbine is a device which will changes mechanical energy, hydraulic energy to mechanical energy. So turbine will convert hydraulic energy to mechanical energy, and the pump will do the reverse action of that. That means from mechanical energy to hydraulic energy. So coming to the turbine, this is a device which is used to convert hydraulic energy to mechanical energy. So where we get that hydraulic energy? So to understand that, we need a support of layout of hydroelectric power plant. So here is the layout of hydroelectric power plant. We already discussed that potential energy was stored in water. So if water is stored up to a particular height, there will be a lot of potential energy stored in that. So we know that the basic equation of potential energy is mgh. So if the height of a water is increasing by using a dam structure, obviously a potential energy will be developed. That potential energy is responsible for turning of turbine blades. So that potential energy is to be converted as kinetic energy. So by using a nozzle setup. So here we can see that different components of a hydroelectric power plant. So here this is a dam structure. So dam is a wall-like structure which is obstructing the water flow. So dam is used to store the water. Because of the storage of the water, potential energy will be developed in the water. So hydroelectric power plant will consist of another component like penstock. So penstock is a large diameter of a pipe, which is used to carry water from source of a water. That means dam structure to turbine starting point. So here we can see different components of a turbine. In the middle of the turbine there is a rotating part. So that rotating part is known as runner. So on the circumference of a runner, we have a blade like structure. We are calling that as a vanes. So there are few important terms in a layout of hydroelectric power plant. In that, first one is a gross head. So gross head is the total head available at the dam structure. So it is to be taken as the difference between head raise level to tail raise level. Tail raise level is the ultimate water venting out point and head raise level is the highest peak point in the dam. The difference between head raise level and tail raise level will be considered as a gross head. And apart from that, here we can see another component also, that is a net head. So net head is the head available at the end of the penstock or at the entry of the nozzle. So nozzle exit point, we will be having a head that is entirely different from a gross head available at the dam structure. So because of the traveling, we know that there is a lot of friction losses and other losses will be takes place when a flow is happening through a pipe from one section of a point to another section. So the losses includes major loss and minor loss. Major loss is due to friction and minor loss is due to different criteria. So that is exit from the pipe, entry in the pipe, exit from the pipe, entry in the pipe, and when the pipe is suddenly enlarged, when the pipe is suddenly contracted or any obstruction in the pipe. So these are the reasons why we are getting a minor losses. But while calculating net head and net head from the gross head, we will consider only major loss. So major loss is due to friction. So here this is the formula which is used to calculate major loss, that is 4FL V square by 2GD. We are much aware of this formula. Here F is the friction factor, L is the length of the penstock, V is the velocity in penstock, G is acceleration due to gravity, and D is the diameter of the penstock. So these are the terms which are used to calculate major loss. Like I already told you that major loss we need to subtract from the gross head to get the value of net head. So here there are other component also. So that is a penstock. So we already discussed penstock is a large dia pipe which is used to carry water from the dam point to a turbine entry point, and here we can see a tile race level. So whatever the water that is exerting from the nozzle will be striking the turbine and will be like deposited at some other place known as tail race level. So these are the few important points of layout of hydroelectric power plant. So what is a gross head, what is a net head, and what is a total head loss? So these are the important terms. Gross head is the head difference between head race level to tile race level. Net head is the difference between gross head level to like subtracting major losses. So major loss formula is 4FLV square by 2GD. So we need to calculate the major loss present in the penstock and we need to subtract it from the gross head to get the net head value. So coming to the classification of turbines. So coming to again, like what is a turbine? Turbine is a device which is converting hydraulic energy to mechanical energy. So hydraulic energy is the energy present in the dam structure. So that energy cannot be directly directly converted as a mechanical energy. Hydraulic energy need to be converted to like a kinetic energy first. That kinetic energy is responsible for rotation of the turbine. So here we can see that the end of the penstock is provided with a nozzle. So nozzle is a device which is having very less cross-sectional area compared to the penstock dia. So when the cross-sectional area is suddenly reduced because of the from the continuity equation, Q is equals to area multiplied by velocity. When the cross-sectional area for a continuous flow is reduces, velocity is strongly increases. It will develop high velocity. So that is the responsible for forcible Z. So Z is like a flash of water. It is a splash of water which is coming out of the nozzle. So which is having more and more velocity. That increasing velocity is due to because of the reduce in cross-sectional area. So when jet is striking this particular runner and vane setup, jet possesses a lot of kinetic energy, and that kinetic energy is responsible for rotation of the runner along with vanes. So because of this work done, so whatever the work done will be there, that work done per second will be considered as a runner power. So runner power is calculated as a work done per second, and that work done per second is the mechanical energy produced by the rotation of the turbine. And this mechanical energy further will be converted as an electrical energy. So that is a different thing. So we need to know before getting into that runner power and shaft power, we need to understand different classifications of turbine. So classification of turbine is much important while selecting turbine for any particular criteria. So first of all, like a turbine classification is mainly due to type of energy available at the inlet. So from the basic layout of hydroelectric power plant, we discussed that end of the penstock is provided with a nozzle setup, and that nozzle will be useful in converting hydraulic energy to kinetic energy, and further that kinetic energy is responsible for mechanical energy. But in all type of turbines, so nozzle will not be there. Few type of turbines, it is essential to convert the entire potential energy to kinetic energy. In few cases, there is no need of converting the entire potential energy to kinetic energy. So that was discussed at the topic of like the classification of turbines. So for coming to the first classification of the turbine, according to the type of energy available at the inlet of the turbine. So inlet of the turbine is nothing but it is a point where jet is striking the turbine. So there, what is the type of energy available? So based on that, turbines will be classified as two basic types. One is impulse turbine and second one is reaction turbine. Coming to the impulse turbine, in impulse turbine, whatever energy, whatever potential energy is there, entire potential energy is converted as kinetic energy only. Entire potential energy will be in the form of kinetic energy only. So here it is in the terms of like a kinetic energy only. In case of reaction turbine, the total energy available is the sum of kinetic energy and potential energy also. So how this will be possible? So let us discuss on that. So kinetic energy. So to convert a kinetic energy, we know that the basic formula of a kinetic energy is half mv square. So here velocity plays a vital role in developing kinetic energy. So how if the velocity of a flow is increases, kinetic energy will be obviously developed. So by providing nozzle setup. So in impulse turbine, nozzle plays a vital role in developing kinetic energy. Whatever the potential energy that is present in the dam is carried to the point of the entry of the turbine through a large dia pipe known as penstock. The end of the penstock is fitted with a nozzle. So the end of the penstock is fitted with the nozzle, responsible for improving kinetic energy of a nozzle. So that nozzle is responsible for improving kinetic energy, and that kinetic energy helpful in rotating the turbine. So in turbines, like where we are providing the nozzles, so they are referred as impulse turbine. So once again I am repeating. So impulse turbine is a turbine where we have the entire potential energy is converted into kinetic energy by providing nozzle at the end of the penstock. And the second one is a reaction turbine. So in reaction turbine, the energy is in the form of kinetic energy and potential energy also. How it is possible? Let us discuss. So kinetic energy will be developed when the cross-sectional area is reduced so that the velocity is increased, but the potential energy will be maintained in a closed circumstance. So coming to the reaction turbine, so reaction turbine doesn't have any nozzle setup, but how the kinetic energy will be developed? So along with the runner vane, so there is a there is a guide vane setup also there in case of a reaction turbine. That guide vanes are reducing cross section of the entire closed setup so that the velocity will be reducing, and it is responsible for developing kinetic energy. So coming to the potential energy, as in case of reaction turbine. So in case of reaction turbine, it is in the closed setup. So reaction turbine are in the closed setup. In that closed setup, so the vanes are rotating. So there is only a set of runner vane mechanism is also there. Runner vane mechanism is also there, and to guide this, the water will be passed through guide vane mechanism. So this guide vane mechanism, whatever water entered through the penstock, so that is entered to the guide vane system first. So that from that guide vane system, so water will be entered into runner vane mechanism. So as this is a closed one, so in this closed one, part of the energy is maintained in the form of potential energy, and because of this guide vane mechanism, because of the reduction in cross-sectional area, part of the energy will be converted as kinetic energy. So coming to the example of an impulse turbine, so impulse turbine example is a Pelton wheel turbine. So Pelton turbine will consist of, as usual, the runner vane mechanism along with the core part, but Francis and Couplon turbine, so there is a guide vane mechanism also. So this is the basic classification of turbine, impulse turbine and reaction turbine. So impulse turbine it requires a high head and low rate of flow, but in case of a reaction turbine, it requires a low head and high rate of flow. So moving to the other type of classification of turbines. So according to the direction of flow through the runner. So here there are like 4 types of turbines. So first one is a tangential flow turbine, radial flow, axial flow and mixed flow. So coming to the first one, tangential flow. If you take a turbine, so if you take a turbine vane like this, so if the jet is striking to the tangent of this particular, so if the jet is striking tangential position of a vane, so it is referred as tangential flow turbine. In case of a Pelton turbine, the jet is striking at the middle part of a wave, that is at the tangent, because that is the reason the inlet velocity triangle is a straight line in case of a Pelton turbine. Second one is a radial flow turbine. In case of a radial flow turbine, so the flow is entirely occupying the radius, complete radius of the wave. So Francis turbine is an example for radial flow turbine. So third one is the axial flow turbine. In axial flow turbine, so the turbine is rotating in horizontal direction. So the flow will be like acting on the vanes in the axis of the direction of the turbine. So that is why Kaplan turbine is a axial flow turbine, and the last one is a mixed flow turbine. So it is a combination of like any 2 types of flows of turbine. So this is again the classification. So turbines are classified based on the energy available at the inlet only. So this is the basic one. So coming to the reaction and impulse turbine again. So we already discussed that like impulse turbine possesses only kinetic energy. So this is due to nozzle setup provided at the end of the penstock. And reaction turbine is a combination of potential energy and kinetic energy. Kinetic energy is developed due to guide vane system. And potential energy is due to a closed system. So the vanes are provided in a airtight closed system. So the reaction turbine will be it is possible to maintain that particular state. So moving to next, so here is the difference of impulse and reaction turbine again. So here if you observe, so the jet is striking the vanes in this direction and it is rotating. So here the middle one is known as impeller. So the vanes are bound on the circumference or in the peripheral direction of an impeller. So here the moving buckets is possible in this direction. So when the jet is striking, it starts rotating, so that the mechanical energy will be developed. So whatever the runner power will be there, so whatever the work done per second because of this movement, so we know that like work done will be equals to force in that direction, force exerted in that direction multiplied by velocity. Force exerted in that direction, that means is it x direction or like a radial direction, anything. So force exerted in that direction multiplied by velocity of the wave will be referred as the work done per second, and that work done per second is known as runner power. Work done per unit time is referred as runner power. This runner power is further treated as a further classified, further like calculated with the shaft power also. So here the reaction turbine, in reaction turbine there is no nozzle. Like water will be entered through guide vane mechanism. So because of that rotating nozzle system, so the water will be travelled through the entire radius of vane, so which is the radial flow condition. So next classification of a turbine according to the head at the inlet of the turbine. So based on this there is a high head turbine, medium head turbine and low head turbine. So based on the country's condition, like the head is different. So based on the head available at the inlet of the turbine, so high head turbine is the Pelton turbine. So Pelton turbine has a high head in the world up to like 1750 meter. So for a medium head, like a Francis turbine can be used, and for low head turbine, Kaplan turbine can be used. And the next classification is classification based on specific speed of turbine. So we need to understand first of all what is a specific speed. So specific speed is very important characteristic. Specific speed of turbine. So specific speed is referred with the letter NS. Okay. So NS, like specific speed, is a very important characteristic in case of a turbine. So it is a speed of a turbine. It is a speed of turbine under specific conditions. So what are the specific conditions? We know that the turbine will be rotated. We know that the turbine will be rotated like this. So we need to provide some inlet energy or input energy, and we will get the output power. We need to get a output power. So if we are providing like 1 meter head, whatever the head we are providing from the dam by using penstock and nozzle, etc. So that is the inlet and input energy we are providing to the turbine. If we are providing like 1 meter head and the turbine was supposed to produce 1 kilowatt power. So this is the condition. These are the two specific conditions that needs to be maintained for the rotation of the turbine in specific speed of a turbine. So specific speed is the speed of a turbine at which with the inlet energy of 1 meter head, and the turbine was supposed to be produce 1 kilowatt power. By satisfying these two conditions, how much speed is maintained by the turbine is nothing but the specific speed of the turbine. So based on the specific speed also, so the turbines are categorized as low specific speed, medium specific speed and high specific speed of turbine. So Pelton turbine is a low specific speed, medium specific speed is the Francis turbine, and Kaplan turbine is maintaining high specific speed. So here we can see type of runner and the specific speed. In Pelton turbine also, so there will be like 3 types of runners will be there: slow, normal and fast, and corresponding specific speed values are given here for all the 3 types of turbines and for the 3 types of runner. In case of a Pelton turbine, if it is a slow type of runner, the specific speed of 10 to 20 will be maintained, and for a Pelton turbine, if it is a normal type of runner, so the specific speed is maintained between 20 to 28, and similarly for the fast it is maintained up to 35. The same kind of a criteria is also maintained for the Francis turbine also. So last one is according to the disposition of turbine shaft. So here it is a horizontal shaft and vertical shaft. So vertical shaft will be there for Francis and Kaplan turbine, and horizontal shaft will be there for Pelton turbine. So next one is like classification. This is the overall view of classification of turbine. So how Pelton, Francis and Kaplan are categorized. So Pelton turbine is an impulse turbine, so which has a kinetic type of energy, so which has a head value from 250 meter to 1000 meter, and it can have only low discharge value, so whose direction of flow is a tangential and have a specific speed of 35 to 60. Similarly, Francis and Kaplan turbine are the examples for reaction turbine. So Francis is the medium head turbine, like which has 60 to 150 meter head, and Kaplan turbine has a less than 30 meter head. So the corresponding criteria is also we can observe here. So Francis turbine mixed flow condition will be maintained, and also radial flow conditions is also maintained. So this table is complete gist of classification of turbines. So here we can see the Pelton turbine with different parts. So here this is the penstock. The end of penstock is provided with the nozzle. So Pelton turbine has a bucket shape of double semi-ellipsoidal. So it has a shape like this, double semi-ellipsoidal shape. So the jet is striking at the mid place of the particular way. So this particular place, this cutter is cutting this jet into 2 equal parts, and it is leaving the vane like this. So the inlet velocity or velocity triangle of a Pelton diagram, Pelton wheel is a straight line, and at the outlet we will be having the velocity triangle, whatever with the components we are having, just like that VW, VR, VU, etc. So these are, we are much conversant with these terms in the impact of jets topic. So here are the other parts of the Pelton turbine. So spur rod is used to control the discharge, and here we are having a hand wheel system to rotate that spur rod. So here is the tile race level, and usually it is not a closed one as it is a open to atmosphere. A casing is provided on the top of the vanes to avoid the splash of the water. So this is the runner vanes. So this is the runner, and these are the runner vanes, and here we can see a tile race also, which is used to collect water, that is after striking the jet. So this is the original picture of a Pelton turbine. Here also we can see that there is a striker, there is a cut like thing in the middle of the vane. So Pelton turbine having a shape of Pelton turbine vane having a shape of double semi-ellipsoidal. So for striking the jet, we will be having a cut like thing in the middle of the vane. Here also we can see a cut like thing. And the next one is efficiencies. Efficiencies are much important in turbines topic or hydraulic machines topic. So there are three types of, especially there are three types of efficiencies. One is a hydraulic efficiency, which is represented by using delta H, eta H, and the second one is mechanical efficiency, eta M, and the overall efficiency, eta naught. So these are the different types of efficiencies that are discussed in hydraulic machines. So before getting into efficiencies, we need to understand different powers. So the different powers which are used in these terms are like a runner power, water power, and shaft power. So there are three powers will be there. So in order, if we are talking in an order, so first one is a water power, and second one is a runner power, and third one is a shaft power. So these are the three important powers in hydraulic machines. So first one is a water power. Water power is the power available in the water. So where water will store? So water will store in dam. So from dam, so whatever the net head will be there, whatever the gross head will be there, we won't consider that. Only the net head we will be considering. So based on that net head, so how much water power will be generated? So water power will be equals to gamma multiplied by Q multiplied by H. So this is the formula for water power. So where we already know that like gamma is the unit weight of water, and Q is the discharge available at the inlet of the turbine, and H is the net head that is available at the inlet. So water power will be calculated by using that formula. So that much of water power we are exerting at the end of the vane. So at the end of the nozzle and at the starting point of the vane. So this is the striking. This is due to striking of the jet. But when the water is leaving from the jet, so some power will be generated because of that mechanical energy. So that is what we discussed as work done per second, work done per unit time, or work done per second. So this is calculated by using formula Fx multiplied by U. So Fx is the force exerted due to the jet, and U is the velocity of the wave. So whatever this work done per second, whatever this mechanical energy is developed, so that is known as runner power. This is due to running of the turbine. So that is the reason it is referred as runner power. And the last one is a shaft power. So shaft power is a power which is available at the end of the runner that is connected to the shaft. So here we are discussing the three types of efficiencies: hydraulic efficiency, mechanical efficiency, and overall efficiency. So coming back to the topic once again, so this turbine impeller is connected with runner mechanism. So the runners are strike with water jet. So whatever power available here is known as a water power. This water power is splashing the jet. So splashing the jet, and the runner will be rotated. So whatever the power that is generated at the end of the runner or blade is known as runner power. So which includes fuel losses, and that losses will be calculated in terms of a hydraulic efficiency. and this power, so whatever the runner power, so this is calculated by using the formula Fx multiplied by U. So this runner power is further converted, conveyed to shaft. So that shaft power is the ultimate power generated by the turbine. So here hydraulic efficiency includes hydraulic losses between the entry point of the vane and exit point of the vane. So it is calculated as the ratio of runner power to water power. Here runner power is the output energy by considering only hydraulic losses. So here it is the output power and the input power is the water power. So coming to the next type of efficiency. So next type of efficiency is the mechanical efficiency. So mechanical efficiency includes the mechanical losses which are presented at the after point of a runner and the before point of the shaft. So from runner to shaft, so there will be few mechanical losses will be there. So between these points, so here the runner power will be transferred. Whatever the runner power that is generated before, so that is transferred to shaft here, and which will include a few mechanical losses. So that mechanical losses are treated based on like a mechanical efficiency. So mechanical efficiency is the ratio of shaft power to runner power. So coming to the last one, overall efficiency. So overall efficiency is the ratio of shaft power to, so it is the ratio of shaft power to water power. We already discussed that shaft power is the ultimate power. It is the output power generated by a particular turbine, and water power is the input power that we are providing to rotate the turbine. So shaft power is the ultimate ratio of output power to water power. Here the output power is referred as a shaft power and input power is referred as a water power. So not only this, we can calculate overall efficiency by using a formula of product of hydraulic efficiency to mechanical efficiency. And this overall efficiency includes both hydraulic losses in terms of hydraulic efficiency and also mechanical problems including mechanical efficiency. So this is the product of hydraulic efficiency and mechanical efficiency will be considered as overall efficiency. So in our today's lecture, we covered basic introduction to hydraulic machines, including layout of hydroelectric power plant. So various classification of turbine, that is impulse turbine, reaction turbine, tangential flow turbine, and based on specific speed how we can classify the turbines, and also like different efficiencies and different powers such as runner, water and shaft power, hydraulic, mechanical and overall efficiencies. So these are the topics covered in the today's lecture. Thank you.